Right. I welcome you guys to this session. And this session will see us through a topic called vector mechanics. It is not a one-day session, but by the end of the session, we should be able to know under what categories is vector mechanics, how do you categorize the vector mechanics, and still we should be able to know what it all concerns with the vector mechanics. So this topic comprises of mainly the following. We shall look at relative motion. It has relative motion. The topic includes shortest distance and time taken. Shortest distance and time taken. The topic involves intersection of paths. The topic involves collision of the bodies. The topic involves crossing the river. Or flying in space. So all these, we shall cover them one by one until we get done with them. I guess in 6 lessons or 7, we should be in position to complete all this topic. Now, we're going to begin with relative motion without wasting any single minute. So, relative motion. And under relative motion, it also comprises of 2 sections, and we shall have relative velocity. We have relative velocity, and we also have relative path. So we are going to look at these 2 first. Okay, and I'm going to be attempting my questions using the simplest approach, that is the vectorial approach. There is geometrical approach, but I'm looking at how tedious it is to some extent, and I'm looking at how simple mechanics of vectors is if one has known how to resolve the forces. So now for this case, I am going to specifically start with the relative velocity. Relative velocity. Now, under relative velocity, I want to first give you a word of encouragement. This topic, students have the phobia towards mechanics, but I really don't see the reason as to why. Because this is something you read and you see happening, and then you sketch what you see happening, and then you come up with a solution to the problem. So, members, now when we say relative velocity, I want you to take a flashback when you are still young, especially when you're being driven into a vehicle. Along the road, you'll be seeing particles moving as if they are following you, okay? As if they are following you. So when you're looking at them and you're looking at your soul, you're looking at them, they are as if they're moving with you. They are moving with apparent velocity to you. So when we say relative velocity, I want you to look at it as the apparent velocity. All right? I want you to look at apparent velocity of one moving object as regards to the other. Okay? Apparent velocity of one moving object as regards to the other. We are not going to ask you for the definition, but I want you to just look at it naturally, and you see how it really happens. Now, we are going to suppose, I want to bring out the main issue. I want to bring the main issue of how it happens. I want you to suppose, particles A and B. Okay. If we suppose particles A and B, and if we suppose that they're in motion, okay, A will appear to be moving with some velocity. I'm supposing that these two particles are moving. So A will appear to be, or to be A will appear to be moving with some velocity, which is not true velocity of A. And that velocity is denoted as AVB. Velocity of A relative to B. Some books, you find VAB. Still, this is the velocity of A relative to B. So that velocity, we are meaning velocity of A relative to B. Okay, that is what we are calling relative velocity. Okay, so we have to use two approaches, as I've told you, to find these velocities or the true velocities. We have to use two approaches. The first approach is the geometrical approach, which I told you that we are rarely going to be using it because I see the vectorial approach is very fast. It gets the answer very fast. Now, with the geometrical approach, we ensure that the velocities of moving objects originate from a common point and their relative velocity causes them to form a triangle of velocities, okay? They originate from a common point and the relative velocity crosses them. The relative velocity crosses them to form a triangle of velocities. So if we have O, this is the common point where they originate, B, okay, let me say AB. If this is VB, the rest of B, and this is VA, the rest of A, it means they are all originating from a common point and their relative velocity crosses them to form a complete triangle of velocities, RV. So if we need RV, RV is AVB, or the relative velocity. So thereafter, we can use the cosine formula or the sine formula to obtain unknown variables or quantities. Or one can use the vectorial approach. With vectorial approach, we ensure that if particle A is moving with the velocity VA and particle B is moving with velocity VB, okay, then the velocity of A relative to B is denoted as A VB and is equal to velocity of A minus velocity of B. Similarly, the velocity of B relative to A is the same as the velocity of B, begin with what begins here, minus velocity of A. I want you to know that velocity of A relative to B has never been equal to velocity of B relative to A. So they are not equal. Do not ever confuse the formulas. Now, with this, you need to know that vector, rather velocity is a vector quantity. So it has got both magnitude and direction. So it is always important to find the magnitude and the direction if asked to find velocity. Do not stop on getting velocity only. Go ahead to get for last the magnitude of that velocity. So now to be realistic to you, when we are using the vectorial approach, we have to summarize so that we don't get issues with question seeming to be tedious. Now, I'm going to give you some examples. We are going to do examples here together. After doing these examples, you should be in position to answer some guiding questions that I am going to leave behind for you. Okay, so now the first question, ship A is steaming due north at 40 kilometers per hour, whereas ship B is steaming in the direction north 30 degrees east at 30 kilometers per hour. Find the velocity of A relative to B. Find the velocity of A relative to B. I'm going to specifically be using vectorial approach so that the question seems to be very easy for us, okay? Because this, the vectorial approach has got fewer steps to take, and then you get the answer very fast. Very fast. So the solution to this question, it's better you first summarize what you're given. And if you have summarized what you're given, we shall have vector, we shall have direction, we shall have the magnitude. Vector, we have velocity of A, direction is north, the magnitude is 40 kilometers per hour. This is a summary that enables you do the sketch with a lot of ease. Then we have velocity of B, direction is north 30 degrees east, magnitude is 30 kilometers per hour. They want us to get velocity of A relative to B. So they want AVB. We don't know the direction. We don't know the magnitude. So by mere having this, you can easily sketch and find what you asked for. For A, the sketch is very easy. They told us that ship A is steaming due north. It means that due north at 40 kilometers per hour, 40. So it means that velocity of A is, if it is north or south, we use J. If it is east or west, we use I. So this is the 40 J. In other words, if I'm to show you the background, this is positive I, this is negative I. This is positive J, this is negative J. As simple as that. So if you have due north, it means that we are having positive J. So it is 40 J. That is velocity of A. Then velocity of B. For B, you have to be smart with the sketch. They're telling us north 30 degrees east. North 30 degrees east. Now, for this case, we have to draw our compass This is our north, and this is our east. So they are telling us north 30 degrees east. So if they say north 30 degrees, it means that after north, I have, this is the north line, I have to count code 30. So this is 30. So, meaning one can resolve with respect to this, or one can resolve with respect to this angle down, which is 60. So you can complete your triangle. So it means that here, if the magnitude of the velocity was 30 kilometers per hour, its components will be 30 sine 60, that is if at all you resolve with respect to 60, or it will be 30 cos 60 degrees. This one, it means that this velocity has got two components. It has got the vertical component, the horizontal component. The moment there is an angle, the moment there is an angle between the magnitude, then you have to resolve the components with respect to that velocity. However, we are going to see how best, and this one will promote our sharpness towards resolution of the forces. So this is what we are having, and now we can get the velocity of B. Someone who didn't want to use a 60 would complete it like this, and you resolve with respect to 30. Okay? But this one seems easier. So velocity of B is the horizontal component, which is on the adjacent, that is 30 cos 60I, with, now we have to add this component, 30 sine 60J. All right, we know cos 60 is a half, so times 30, that is 15I. And you know sine 60 is √3/2, which will reduce with this 30 to make 15√3J. By subs, sine 60 is √3/2, but a 2 will reduce the 30 and remain with 15√3. Now, they need velocity of A relative to B. So AVB is the same as velocity of A minus velocity of B, which is equal to velocity of A is 40J minus velocity of B, which is 15I, plus 15√3J. So this is the same as 40J. Of course, we shall have negative 15I, correct like terms. Then this is 40J, okay? 40J minus 15√3J. So this will give you 14J. So, meaning that the magnitude of AVB, because the velocity must have magnitude and direction, so it will be the square root of 15 squared negative 15 squared plus 14 squared, which is equal to the square root of 225 plus 196, which gives 20.05 kilometers per hour. This is the magnitude, but it has got direction too. It has the direction. So getting the direction, to get the direction, what do? Direction. You need first sketch using this velocity, negative 15I. If it is negative 15I, then it means that you're moving this side. Negative 15I is this side, so this is negative 15I, but because we have already shown that it is in the negative side, just say 15. Then 14J, let me sketch it from this side is 15I, negative 15I and 14J. So negative 15I is this. Then positive 14J. Then you complete. So this is the magnitude of the direction we are having, which is 20.05. So to get that angle theta, we shall use tan, which will be opposite 15, sorry, which will be 14 out of 15. So you can get theta as tan inverse of 14 out of 15. Alternatively, someone who sketched like this would also be fine. Negative 15I and positive 14J. You move like this, so 14. Still, this person would be fine. So this is your resultant, 20.05. So it would mean that here the tan theta would be equaling to 15 over 14. And you get your theta as 47. But then you would conclude, you have to conclude that therefore, the velocity of A relative to B, velocity of A relative to B is 20.05 kilometers per hour in the direction, first mention north, in the direction north, 47 degrees, then west. North, then west. So we are going to do very many examples that are going to activate your understanding of this topic. Let's do number 2 and we see. Number 2. Car A is moving due east at 60 kilometers per hour, whereas B is moving in the direction north, 60 degrees west at 50 kilometers per hour. Find the velocity of A relative to B. That is what we are having. Still, you sketch. But to summarize all, we shall have a vector, shall have direction, we shall have magnitude. We have velocity of A, we have velocity of B, we have AVB. Velocity of A as is in the direction east. While for B, we're in the direction north 60 degrees west. While for this, we don't know. Magnitude here, we have 60 kilometers per hour. And with this, we are having 50 kilometers per hour. Here we don't know. So you can sketch very fast. For A, the particle is moving, or the car is moving due east, okay, at 60 kilometers per hour, meaning that velocity of A is positive 60 I. That is the mark. Then for B, north 60 degrees west. North 60 degrees west. So this is my north line. $60, you count 60 degrees, this is north, but you will count 60 degrees to the west. So this is north, and this is 60 degrees, but to the west. So my components will be like this. Otherwise, even one would have used a 30, but it depends on how easy you can resolve this. So this is 50, the magnitude of this force is 50. Magnitude of the velocity is 50. So it implies that, now for this case, you can see that this is the adjacent. The adjacent always will take the cos component. So this is the adjacent, and this will be 50 cos 60 degrees. And this will be 50 sine 60 degrees. 50 sine 60 degrees. I'm going to give you an alternative of this diagram because one even can use a 30 to resolve this component. So it would mean that the velocity of B is equal to, for this case, it is going to be this one being in the negative I, this will be the I side. So we shall say negative 50 because it's in the negative. Negative 50 sine 60 degrees I plus, this is in the positive side, plus 50 cos 60 J. And looking at this, sine 60 is √3/2. So this is negative 50 times √3/2I plus cos 60 is a half times 25, that is, rather times 50, that is 25J. Or else, one would have drawn this like this, okay? You have your north line. This would be 50, rather you measure 60 degrees. This would be 60 degrees. Okay, so instead of using this component, one can as well use the 30. One can use the 30. So one can use the 30 degrees here. And when you use the 30 degrees here, now it means that this one will be the cos. Because this is where you have the adjacent, this is our adjacent, an angle and the 90. So this will be 50 cos 60i, and this will be 50 sine 60, rather sine 30. Now there you use a 30. Sine 30, sine 30. Then as you're writing the component, you will say velocity of B is equal to, you can say 50 negative the cos 30i plus 50 sine 30j. Cos 30 is root 3 out of 2. So this will be negative 50 times root 3 out of 2i, then plus 25j. As simple as that. So still it is the same. So the components always depend on what you want to use. Now, AVB, they need AVB, but you know that AVB is the velocity of A minus velocity of B. So velocity of A was 60i minus negative 50 root 3 over 2i plus 25j. So this is the same as 60 plus, because this will be plus 50 root 3 over 2, everything I, then minus 25j. So this is 25 root 3, so this is 60. Right? Plus 25 root 3 I minus 25j. This one, 60 plus 25 root 3. 25 root 3. This will be 103.3i minus 25j. That is my AVB, but it must have the magnitude. So AVB would be equaling to the square root of 103.3 squared plus negative 25 squared. And this is going to give me the square root it will be 106.3 kilometers per hour. .3 kilometers per hour. Okay. So having gotten that, you need to go ahead and look for the direction. To get the direction, you have to sketch the component, this component. So to get the direction here, you would have 103.3i, which is positive. So we have positive 103.3, 103.3. Then negative j, because we have negative 25j. So one can move this side to negative 25, or you can draw the positive j, but then you move down like this. So this is 25j, but you don't put a j, just say 25. Then you complete. So we are looking for angle theta. And this is our magnitude. Sorry, this is the same as this, 103.3. So you can say tan theta is equal to opposite, that is 103.3 out of 25. And you get your theta as the tan inverse of 103.3 out of 25. So here, you happen to get your theta as 76.4 degrees, and you conclude. Otherwise, someone can use, someone would sketch this still as you would sketch positive 103, then negative immediately. Then still you'd be in the same line. So one can conclude here and say, therefore, the velocity of A relative to B is 106.3 kilometers per hour in the direction you first mentioned south, first mentioned the J, in the direction south, 76.4, then east. Because you mentioned south, then east. As simple as that. As simple as that. Let's do number 3. The more examples we do, the more you understand this work better. The more examples we do, the more you understand this work better. To a cyclist, riding